So we'll start with today's class. So this week you see most of few substances how to calculate enthalpies for mixtures of vapor and liquid in two-phase region, and how to use see some examples on compressibility using compressibility chart, how to calculate, and so on. Examples regarding that. If you have any queries in the previous weeks or in this week, you can ask, uh, or else you can move forward with problems. So okay. So the first one, I think, this problems regarding this your compressibility factor, how to solve that. So I'll first explain the chart, how what is this, and compressive factor is Z, is represented by Z, and it is equal to PV by RT. So if you see the blue circle region, that is your two-phase
Sir, very
region.
good evening to you, sir.
Yeah. Good evening. Good evening.
Sir, actually today I am in train and I am just journey from my college to my home. So today I'll not be able to interact with you more. Okay, sir.
No issues. If even if you have any doubt, you are
But
not
I
able to
will
speak, you can
I will
you can
listen
put
the
it in the
class
comment.
carefully. Okay, sir.
Yeah, you can put a comment if you are not able to speak. If you have any queries, you can put in the chat. I'll
Sure,
reply.
sir. I will just listen the class. Okay, sir.
Okay, okay.
Thanks a lot, sir.
Yeah. So the compressibility Z, it's plotted in the y-axis, and you have PR. PR is the pressure ratio with respect to the critical point. It's called reduced pressure here. So and you have this blue line in a semicircle, you could say, kind of an elliptical half. So that is your two-phase region. This represents your two-phase region. So for any given pressure, so you have saturated vapor and saturated liquid, and inside you have a mixture of both the liquid and vapor at different fractions. And for the given condition of PR equal to zero point 0.2, this is a logarithmic curve, and for that the TR is given as 0.78. So you have other two lines of reduced temperatures which has been plotted. One is 0.7, so and another is 2. So 2 signifies your twice the critical temperature. So if TR is 2, it is 2 times of critical temperature. So you have multiple family of curves which will be plotted in this Z, and you can use this to find out the compressibility factors for a given pressure and temperatures. So you will know for a given fluid, you know your critical temperature and critical pressure. Using that, you can find out this PR and TR. So using that, you will have a set of curves to represent it, and you can straight away find a compressibility factor Z. So we'll see how this is used to calculate. So example is propane is there in a steel bottle, so whose volume is 0.1 meter cube. They say its quality is 10% at a temperature of 15 degrees Celsius. So 10%, so 10% volume, and the 90% is liquid. Use the generalized compressibility chart to estimate the total propane mass and to find the pressure. So this compressibility chart general came because the ideal gas are whatever fluid which we have, it will not it will be ideal mostly at low pressures and very high temperatures. So in that case, there will be very less interaction between the molecules. So but in actual scenarios we will deal with this, this will not uh, follow this ideal gas equation. So these are all some of the ideas which people came up with to solve, to overcome and handle real gas. So this propane is at 15 degrees Celsius, and your volume is given and quality is given. Now we'll see how to calculate the pressure and the propane mass which is there in the cylinder. So for a propane, the critical pressure is 4250 kilopascal, or you can say 42.5 bar, and critical temperature is 369.8 Kelvin. So from this we can find the reduced temperature. So reduced temperature TR is T by Tc. So we substitute T value. T is 15 degrees Celsius, which is given, So 273.15 plus 15 to convert it into Kelvin by 369.8, which is the critical temperature. So we get 0.7798, which is close to 0.78. For the two-phase state, the pressure in the saturated pressure, so P is PR saturated into critical pressure. So saturated pressure is 0.2 into 250 4250 kilopascal, which is the critical pressure. So this we got from the previous chart for corresponding to TR 0.78. So the PR value is 0.2. So hence we use PR sat as 0.2 into PC. So we'll get 850 kilopascal. So now we know that reduced pressure, and we know the pressure in the cylinder, using which we have found out the pressure in the cylinder. Now we can find out the Z factors from the chart corresponding to saturated vapor and saturated liquid for 0.2 and TR is 0.78. So corresponding Z for saturated vapor and Z for saturated liquid is for liquid is 0.035 and for gas is 0.83. And we know that the quality of the fluid is 10%. So if quality is 10%, so X is 0.1. So 0.9, this is you can for two phase. So Z is represented as 1 minus X into Z of fluid plus X into Z of Z is compressibility of gas. So we substitute X, and we know the saturated liquid compressibility factor and saturated gas compressibility factor from the chart. So we substitute that, and we get the total compressibility or the overall compressibility is 0.1145. And we also know the gas constant for propane is R is 0.1886 kilojoule per kg Kelvin, or you can say 8.314 divided by your molecular weight. So we can get a gas constant. So PV equals to M into ZRT. So from this we can find out mass. So Z, we overall compressibility we have calculated. R we know, temperature is 15 degrees Celsius, or 273.15 plus 15 in terms of Kelvin, and we know pressure, which we have calculated as 850 kilopascal, and volume is also given as 0.1. So on substituting that, we will find out that your mass is 12.66 kg. So that's how we calculated mass and pressure from the compressibility chart. So the next question is, a gas bell is submerged in liquid water with its mass counterbalanced with rope and pulleys as shown in figure. So you have a gas bell which is submerged in liquid water, and that gas bell is suspended using pulleys and rope and a counterweight. So the pressure inside is measured carefully to be 105 kilopascal, and the temperature is 21 degrees Celsius. So a volume increase is measured to be 0.75 meter cube over a period of 185 seconds. So what is the volume flow rate and the mass flow rate of the flow into the bell, assuming it is carbon dioxide gas? So initial pressure which is they have given is measured to be 105 kilopascal, and temperature is 21 degrees Celsius. Now there's some mass of CO2 which is pumped in, and the volume increases by 0.75 meter cube during the period of 185 seconds. So now we have to find out what is the volume flow rate, the mass flow rate, and mass flow rate into the bell. So from this we will find out that the volume flow rate is nothing but your change in volume by change in time. So change in volume is 0.75 meter cube divided by, it happens during a period of 185 seconds. So 185. So this will become equal to 0.004054 meter cube per second. So this is the volume flow rate for the CO2. So now we can find mass flow rate. Mass flow rate is nothing but your volume flow rate. So into density will give me mass flow rate, or you can divide it by specific volume to find out the mass flow rate. So at so we assume this carbon dioxide to be a ideal gas. So PV equals to MRT, or a specific volume we can find out using RT by P. So V by M is specific volume, so specific volume is RT by P. And we have the ideal gas constant for CO2 as R equal to 0.1889 kilojoule per kg Kelvin. So mass flow rate we can calculate. So PV, V dot is mass flow rate divided by RT. So 105 into volume flow rate divided by 0.1889 into temperature, 273.15 plus 21, which writing in Kelvin. So this will give me 0.00766 kg per second. So this is the mass flow rate. So moving on to the next problem. So we have a closed rigid container of volume 0.5 meter cube, which is placed on a hot plate. So as shown in the figure, so we have a hot plate uh, which is getting heated, and you're keeping a closed rigid container, so it's kept over the hot plate, and the volume of the container is given as 0.5 meter cube. Initially the container holds a two-phase mixture of saturated liquid So initially the container holds a two-phase mixture of saturated liquid water and saturated water vapor at pressure equal to 1 bar with a quality of 0.5. So we have a mixture of steam or water vapor and water with a quality of 0.5. So 0.5, 50% is liquid and 50% is vapor. After heating, the pressure in the container is P2 equals 1.5 bar. So you are heating, because it's placed on the hot plate, it's get heated up and the pressure changes to 1.5 bar. So indicate the initial and final states on a TV diagram and determine the temperature in degrees Celsius at state 1 and 2, the mass of vapor present at state 1 and 2. If heating continues, determine the pressure in bar when the container holds only saturated vapor. So there are three states you see. So initially you have 50% vapor and 50% liquid, and the pressure is at 1 bar. Being a closed container, the volume will remain same at 0.5 meter cube. So the next case is this is placed on a hot plate, so get heated up and your pressure increases to 1.5 bar. At this case you will have some other fraction which we need to find, and then this being heated up, liquid will evaporate and become vapor. So when it fully turns into vapor, the whole container contains only vapor. What will be the pressure at this state? So this is the three states, and we have to find out the corresponding temperature, pressure, and the mass of vapor. So if you see in a TV plot, this is how it will look. So the first state is you have 1 bar and you have mass of 50% by mass of vapor. So the specific volume will be somewhere here V1, and your volume will remain same. So you are going straight here, because it's a closed container, the volume will remain same, and there is no change in mass, so your specific volume will also remain constant. So from 1 you are going to state 2, which is at 1.5 bar. So previously it was 1 bar and some specific volume V1, and at state 2 you are at 1.5 bar, and now you are at same specific volume, but your fraction will be different. You see from saturated vapor and 1, and your saturated liquid and 1, the fraction, the length between the point and the dome is different. So if you see at higher pressure, you are moving close to saturated vapor. So and when you reach state 3, you are fully at the vapor dome. So you are at the vapor state, saturated vapor state. So we need to find out the corresponding pressure here, and we need to find out the temperature at state 1 and 2, and the mass of vapor which is present at 1 and 2. So at we'll first start by calculating the state 1. State 1, we know volume, we know we can find out specific volume at state 1. So V1 is specific volume at state 1 is specific volume of saturated liquid plus X into your difference in saturated uh, vapor and saturated liquid. Is nothing but 1 minus X into saturated liquid plus X into saturated vapor specific volumes. So if you do that, we initially we will know. Okay, I'll go back. I'll give you the question again as I joined recently. So you see, you have a hot plate. I have kept a container of volume 0.5 meter cube, which contains 50% by mass of vapor and 50% of liquid, and this is at pressure of 1 bar. And then you are as it is kept on hot plate, it will get heated up. Your pressure at state 2 is 1.5 bar, and then you need to find out the temperature between the states 1 and 2. Initially it is 1 bar and 0.5 quality. For that you need to find out temperature, and it's getting heated up to 1.5 bar. You need to find out temperature there, and also the mass of vapor at state 1 and 2. Then you are allowing it to fully convert into vapor. So at state 3 it's get heated up and liquid all converts into vapor. So now the container contains fully saturated vapor. At this point, what will be the pressure? So that's what we need to find. So this is represented in a TV diagram, and that's what in the question it's asked to represent the states, different change in states in a TV diagram. So we are representing a TV diagram because your volume is constant and the mass which is contained in the container will be same. So your specific volume is same. So your V1, V2, V3, your all specific volumes will be same here. So initially we will find state 1. So V1 is represented as Vf1 plus X into change in difference in the saturated liquid and saturated vapor specific volumes. So at 1 bar, your from steam table you can get Vf1 as 1.0432 into 10 power minus 3 and Vg1 as 1.694 meter cube per kg. So substituting this for x equal to 0.5, we'll get the specific volume at state 1 as 0.8475 meter cube per kg. So this will remain same throughout the change in process. So now at state 2, we know the pressure. So the pressure is 1.5 bar. So correspondingly we can find out the saturated vapor and saturated liquid specific volumes from steam table, and it will come out to be 1.0582 into 10 power minus 3, and saturated gas is 1.59 meter cube per kg. So now using the same relation, specific volume is equals to Vf plus X into Vg minus Vf. We substitute the values. We know the specific volume at state 2 because it is a constant volume process. So V2 is equals to V1. So we substitute that and we can find out X. We can find out X. So in this case, we know that specific volume V2, which is there 0.8475, it is lying between Vg2 and Vf2. So that means it is in saturated, it's in a two phase. So you see the specific volume at state 2, it is greater than your liquid saturated liquid state specific volume, and it is less than your saturated gas vapor specific volume. So it says that it is in two phase. So now both state 1 and state 2 are in two phase state. The temperature can be it will be corresponding to the saturation temperature of the fluid, which is water. So from steam table, corresponding saturated temperature corresponding to 1 bar and 1.5 bar we can find out. So T1 is 99.63 degrees Celsius. So you know water boils at 100 degrees Celsius for 1 atmosphere. So this is 1 bar. So it is less than 1 atmosphere. 1 atmosphere is 1.0132 bar. So correspondingly, you see your saturated temperature is 99.63 degrees Celsius. So this is the saturation temperature for 1 bar, and for 1.5 bar you find that T2 is 111.4 degrees Celsius. So we have found out the temperatures. So next is we need to find out the mass of vapor present at state 1 and state 2. So mass can be calculated. We know specific volume, we know the total volume. So that is nothing but specific volume is nothing but volume by mass. So we can find mass. So mass is volume by specific volume. Volume is 0.5 meter cube, which is given. Divide by 0.8475 meter cube per kg, which we have calculated. So mass is 0.59 kg. So this is the total mass, including both vapor and liquid. Now the quality is given. Quality is nothing but mass of vapor divided by total mass of vapor plus liquid. So from there we can find out that mass of vapor which is present is nothing but the quality into total mass. So quality is given as 0.5 at state 1, and total mass we have calculated as 0.59 kgs. So this gives me the mass of vapor which is present as 0.295 kgs. Next is we need to find, we know that the process goes through a constant volume process. So from there we can find out the quality at state 2. So we know the corresponding gas, saturated vapor and saturated liquid specific volumes, and we also know the specific volume at state 2. It will be equal to V1. So we substitute that, and we can find out the quality. So this is just from the first equation, V1 equal to Vf1, we just rearrange it to find out x. So and substituting the values, we will get x as 0.731. So previously it was 0.5, so now the mass of vapor has increased to 0.731. So again we can find out mass. So the mass will remain same because it's a closed system. So x into the total mass, which will give me 0.431 kgs. So now at state 2, 0.431 kgs of water is in vapor state. So now if you continue heating this, so the total 0.59 kg will get converted into vapor. So and correspondingly the specific volume at that state will be 0.8475. So the saturated vapor at state 3, the specific volume of that will be 0.8475, and from the steam table corresponding to this value we can interpolate and find out that the pressure at state 3 will be 2.11 bar. So at 2.11 bar you will reach saturated vapor state, where the whole of liquid which was present will get converted into vapor, and because this is a closed system, your specific volume at that state will be 0.8475, and that will be corresponding to the your vapor state specific volumes. Okay, so moving on to next. So you have water contained in a piston cylinder assembly, which undergoes two processes in series from an initial state where the pressure is 10 bar and the temperature is 400 degrees Celsius. So the process 1 is the water is cooled as it is compressed at a constant pressure of 10 bar to the saturated vapor state. Then process 2-3 is the water is cooled at constant volume of 150 degrees Celsius. So process 1-2 is a constant pressure process, and process 2-3 is constant volume process. Now what they are asking is, the initial state is given as 10 and 400 degrees Celsius. They are asking you to plot on a TV and PV diagram. Then for the overall process, determine the work for state process 1. Both the process for overall determine the work, and for the overall process determine the heat transfer. So from 1 to 3 we need to find out the net work done and the net heat transfer during this two process, the total process. So you see, this is the piston arrangement. You have water. So initially you are compressing at constant pressure from 1 which is at 400 degrees Celsius and pressure of 10 bar. So if you see in a PV diagram, so this is the orange color one is your two-phase region, so a mixture of vapor and liquid. They're saying at 10 bar and 40 degrees Celsius. So this red line at 400 degrees is one is a constant pressure line. So you have from sorry it's a constant temperature line. This is a 400. This is a constant temperature line in the PV diagram. So from 1 to 2 there's a constant pressure process. You're compressing the water to make it a saturated vapor at state 2. So initially at 1 this is at superheated state. So corresponding to 10 bar and 400 degrees Celsius, if you plot in a PV diagram, you will find that this is in a superheated state. So it's what you have is steam. So you are compressing the steam. So during the process, what's happening is the water is reaching saturated vapor state at at point 2. From there, you are doing a constant volume process. So and you are cooling this system. So by cooling to 150 degrees Celsius. So to 150 degrees Celsius, you are cooling from 2 to 3. This is at constant volume. So the corresponding pressure to 150 degrees Celsius, your saturated pressure. So this is 4.758 bar. And the same is shown in a TV diagram. So in a TV diagram, again this orange one is your two-phase region, and this line is a pressure line, constant pressure lines, which is plotted. So at 10 bar, the corresponding saturation temperature is, if you see, is 179.9. So we are at 400 degrees Celsius. So if you see this difference, so it will be in a superheated state. So from 1 to 2, again you are following the constant pressure line to reach saturated vapor, and then constant volume line, TV, so constant volume line to reach 150 degrees Celsius. So we have plotted both PV in and TV. Now we need to calculate the total work done during the process 1 to 3. So 1 to 3, the process net work done we can calculate in two steps. So 1 to 2 and 2 to 3. So if you see, the network is PdV, integration of PdV. So integration from 1 to 2 and 2 to 3. So 2 to 3, if you see, it's a constant volume process. So dV is 0. So you will not generate any work during 2 to 3. So the only work which is generated is during process 1 to 2. So if you integrate, it's a constant pressure process. So you can take outside and integrate. You will get the change in volume. So work per unit mass is P into V2 minus V1. This is specific volumes. From volume you have converted into specific volumes by writing work done per unit mass. So here we know 1 and 2. 1 is 10 bar and 400 degrees Celsius. So correspondingly we can find out your saturated specific volume at state 1, and 2 is saturated vapor. So we can find out specific volume at 2 for same 10 bar. What will be the saturated vapor? So from steam table, V1 is 0.3066 meter cube per kg, and state 2 10 bar saturated vapor is 0.1944 meter cube per kg. So on substituting in the equation, we will find out that the work done is minus 112.2 kilojoule per kg. So this is negative because you are compressing the system. Then second is to find out the net heat transfer which is happening between the process 1 to 3. So we will do an energy balance we can find out an energy balance. So we have found out the total work done during process 1 to 3, and we know we can find out the state points 1 and 3. So we'll apply the first law. So Q minus W will be equals to change in internal energy. So from 1 and 3 we can find out the difference in internal energy of the system, and then we also know what is the total work which is being done during process 1 to 3, which we have already calculated. So we can substitute m equals u3 minus u1 equals q minus w. So we divide it by mass. So q by m equals u3 minus u1 plus w. So u1 we know from superheated steam table that u1 is 2957.3 kilojoule per kg, and u3, to find out u3, u3 is state 3 is in two phase region. After cooling, the saturated vapor condenses and some part of it will be in liquid state. So we need to find out what fraction of it is in vapor state. So for 150 degrees Celsius, we'll find out uh, the saturated vapor and saturated liquid specific volumes, and we know specific volume at state 3 because it's a constant volume process. So V3 will be equal to V2. So we substitute that, and we can find out the quality. At quality will be 0.494. So correspondingly at state 3 we can find out internal energy as internal energy at saturated liquid plus x into the difference in internal energy between saturated vapor and saturated liquid. So we substitute all the values here. We know x, we can from steam table we can find out for 150 degrees Celsius what is the saturated liquid internal energy and saturated vapor internal energy, and substituting that we'll find out that u3 is 1584.0 kilojoule per kg. So on substituting this, we'll find that q by m, heat rejected, is minus 1485.5 kilojoule per kg. So this is the net heat transfer which is happening during the process 1 to 3, or the overall heat transfer. So moving on, the next one is consider a closed system of constant volume containing wet steam. So again, a closed system of constant volume, we have a wet steam. So that is a mixture of vapor and liquid. So the objective is to study the evolution of the thermodynamic state of water during heating from the initial temperature T1 to final temperature T2. So determine the specific volume, the specific internal energy and specific enthalpy at the initial state 1. Determine the specific volume, the pressure, the specific internal energy and the specific enthalpy at final state 2. Then calculate the received specific heat energy during heating. So basically what they are asking you to, they have wet steam inside a closed vessel, you are heating it. What is the properties at state 1, what is the properties at state 2, and how much of heat are you providing to convert from the system from temperature T1 to T2. So that's what basically is being asked. So the data which they have given is initial state pressure is 20 bar and quality is 0.5. Your final temperature is 450 degrees Celsius. At state 2 it is at superheated state, so correspondingly the pressure and volume enthalpy is given at 4 different pressures, specific volume and enthalpy is given. Then saturation state at 20 bar is given, the saturation temperature is 212.37 and corresponding specific volume of liquid and vapor and enthalpy correspondingly to liquid and vapor is given. So H double dash indicates vapor and single one indicates liquid. So this is how the process will look in a TS diagram. So if you see this curve is your two-phase dome and two constant pressure lines are plotted. So initially P1 is 20 bar, which is wet steam. So wet steam somewhere you are lying in between in the two-phase region. From there you are heating it. So you are reaching saturated vapor state, and then this is a constant volume process actually. So this is a constant volume line which has been plotted, and then you are reaching state 2. So this is how it will look in a TS diagram. So from at state 1 we will find out what is the specific volume. So specific volume at state 1 is again you will use the same equation, you know x, which is 0.5, and corresponding to 20 bar the data is given, so saturated vapor and saturated liquid values. On substituting we can find out that specific volume at state 1 is 0.05036 meter cube per kg, and similarly at the enthalpy, overall enthalpy for the wet steam is saturated liquid plus the latent heat. So H, the saturated vapor minus saturated liquid, enthalpy is your latent heat corresponding to that pressure and temperature. So that into X, X is your quality. So this will give me the enthalpy at state 1. So it will come out to be 1852.9 kilojoule per kg. The enthalpy is also is given for saturated vapor and saturated liquid corresponding to 20 bar. So now they have also asked to find out the internal energy. So internal energy is nothing but H is U plus PV. So you can use U is H1 H minus PV. So specific volume is known, pressure corresponding at that point is known, your enthalpy is known. So 1852.9 minus specific volume 0.05036 into 20 bar. So bar you convert into kilopascal because this will be in kilojoule. So 20 into 10 power 2. So substituting that we'll get internal energy as 1752.2 kilojoule per kg. So we have found out the internal energy and specific volume and enthalpy here. The next one is to find out at state 2. So this being a closed vessel, this will go to a constant volume process or isochoric. Constant volume is also called as isochoric. So the final specific volume at state 2 will be equal to same as what we have calculated V1. So V1 is equal to V2. Then we can find out for corresponding to state 2 from the table for superheated steam. So if you see our specific volume value is 0.05036. So it will lie between 60 and 62. So at 60 you see 0.5210 and 62 is 0.05030. So we need to interpolate to find out the pressure at corresponding to that pressure, specific volume, and we'll find out by interpolation using 60 and 62. We'll find out that pressure corresponding to 0.05036 meter cube per kg is 61.9 bar. And then similarly we can find out enthalpy. Similarly we need to interpolate between 3303.5 and 3300.6 corresponding pressure 60 and 62. We know now the pressure, which is 61.9. So using that we can find out the enthalpy, which is 330.7 kilojoule per kg. So we know we have found out both pressure and enthalpy. Again we can find out internal energy as H minus PV. So we know pressure, we know enthalpy. Substituting that we can find out the internal energy, which is 2988.8 kilojoule per kg. So next is they are asked to calculate the total amount of specific heat energy received during heating. So to convert from 1 to 2, how much heat we have provided. So that is nothing but, this being a closed system, if you apply the first law, so Q minus W equals to change in internal energy. There is no work done in the system, so work done is 0. So Q is nothing but your change in internal energy. So specific heat energy which is inputted equals to specific change in internal energy. So U2 minus U1. So we have calculated already U2 and U1. Substituting that, we will find out that we have supplied 1236.6 kilojoules for 1 kg, for per kg of water. To convert it from state 1, which is at 20 bar and 20 bar and to temperature of 450 degrees Celsius. So the next first one is we have a coil through which fluid passes, is immersed in a calorimeter. So this is a problem of calorimeter. So calorimeter, you can find out, you do some process, they will be surrounded with fluid, mostly in this case water. You measure how much is the change in the temperature of the water to estimate. If you can use it to estimate the calorific value of any fuel or oil. And here we are using to estimate CP, the specific heat for hydrogen, and also to find out how much energy is there in the thermal oil. So that's what basically a calorimeter is used to estimate the energy using the change in temperature of the water. So here the problem says you have a coil through which fluid passes and it is immersed in a calorimeter containing water. So it is shown in the figure here. So this is how it will look. So there is a coil which the entry state is given denoted as state 3 and exit is given as state 4. In that inside vessel, this is closed vessel and you have water inside, and this is insulated from the outside. So whatever energy is there lost by through the coil will be gained by this water, and there is no interaction between the surrounding. So this is the general idea of the calorimeter. So they say the fluid enters at constant temperature T3 and exits at the temperature T4. The coil is sufficiently long so that this temperature T4 becomes equal to the temperature TE of the water in the calorimeter. So you have T3, the temperature at which the fluid is coming in. So it will lose energy, or and it will become equal. The temperature is becoming equal to the temperature of the water. So the measurement consists of the following phases. So initially phase 1 is the water of the calorimeter being initially at TEI. The coil is traversed by thermal oil of known specific heat. So we know the specific heats of the oil. So it is given by CL in order to determine the operating characteristics of the calorimeter. So first initially what you are doing is you don't have any data on the calorimeter. So you are using oil which is of known capacity specific heat, and using that you are estimating what you will get in a calorimeter to test and different fluid. So initially you do validation. So this is phase 1 is kind of validation. So you use thermal oil. So initially the water is at TEI, you are passing there, and that is the phase 1. The second phase is same temperature TEI is there in the water. Now you are passing hydrogen, and after time TH, you note that the temperature change of hydrogen is TH4. TH4 means hydrogen temperature at state 4 at the exit of the coil. So what is the data? So they are saying the pressure of the oil and the hydrogen in the coil are constant. The calorimeter is thermally insulated. These are the assumptions which they are making. So there is no change in kinetic energy or potential energy. The calorific value of the wall and material are all negligible. So you need to consider only water. The specific heat of water and oil are constant. So it will not vary with respect to temperature and pressure. That's what they say. So hydrogen can be considered as perfect gas. So again, that means your Cp is constant. As soon as the temperature of the water corresponding to TEI, the temperature drop of the heating fluid is distributed uniformly from inlet to exit. So these are the assumptions which they are making. So the data which they have given is initial temperature of water is at 15 degrees Celsius. The specific heat of water is given as 4.18 kilojoule per kg Kelvin. The mass of water which is contained in the calorimeter is 0.4 kgs. So this is the data of the calorimeter. Now during the phase 1, your temperature of oil at inlet is 80 degrees Celsius. Your specific heat of oil is 1.65 kilojoule per kg Kelvin. Then mass of the oil filling the coil is 0.1 kgs. Mass flow of the oil is given as 10 power minus 3 kg per second. And similarly data here for hydrogen, we know 80 degrees Celsius inlet, outlet is 52 degrees Celsius, and for the time taken is 49 seconds. Mass flow of the hydrogen is 2 into 10 power minus 3, and same mass of hydrogen in coil is 9 into 10 power minus 6, and molar mass of hydrogen to find out R. So it's given as 2.02 kg per kilomole. So this has data given. What we need to find out is the evolution of temperature of water of the calorimeter as function of time. So phase 1, calculate the temperature of water at final state, and after the passage of the uh, initial state, which is at 15 degrees Celsius. You need to find out the final state temperature. So second is, if we instead of passing it to the coil, or if we pour the same amount of mass of oil into the water directly, will we reach the same temperature? So that is the second part. And then for phase 2, you need to find out the Cp of hydrogen. So we'll see how to solve this. So initially, the system, we consider both just the coil and water, and between any change in temperature from time t to t plus dt, we assume that your water temperature is changing from dE to TE to TE plus dTE. So now the change in internal energy is nothing but this being open system, you apply the steady flow energy equation. So H3 minus H4, this is the mass of fluid which is coming in. So M3 mass will be constant of the oil. So M into enthalpy at inlet minus enthalpy of exit will be equal to your change in the internal energy of the system. So this is what will come to the simplified equation, which you will get from the steady flow energy equation. You will neglect the internal energy, the potential energy and kinetic energy, and velocity and potential energy, and then there is no heat transfer between the surroundings. So Q is 0, W is 0. So this is what we will get. So this du by dt equals H3 minus H4 into dm is, there is no mass flow rate, so m dot into dt, any specified time. So your H3 minus H4 can be written in terms of temperature. So m dot Cp T3 minus TL TE. So this H4 temperature is TE because in the problem they are saying that the coil is long such that the exit temperature is equal to the water temperature. So T4 is equal to TE. So TE we have written, and your the internal energy change is nothing but MECE, this is water, into the change in temperature of water, plus MLCL into change in temperature of the oil. So mass of oil in the coil, and C is the specific heat of the coil, and the temperature change in the coil, oil in the coil. So this is the change in internal energy. This will be equal to this change in enthalpy. So from this we can find out the temperature TE, so which is equal to T4. So we can divide it by m dot ECE and CL, so on, and we can find out the simplified expression for TE as T3 minus TEI into we have integrating this with respect to time, so we have to integrate it. So here unknown is TE, so we'll divide by T3 minus TE and we'll integrate it, so we'll get logarithmic terms both sides, and this will be the simplified expression which we'll get later. So final temperature of water of the calorimeter after the passage of mass ml of oil. So TL is mass of oil divided by mass flow rate, so it will take 100 seconds. So and we can substitute that temperature time here to find out the total final temperature. So final temperature will come out to be 20.83 degrees Celsius, because we know so mass flow rate of the oil is known, so mass of the oil flowing in the coil is known. So from there, so it is 0.1 divided by 10 power minus 3, so which is 100 seconds. from there we have found out time, and the other known is 80 degrees Celsius, which is T3, and your water temperature, which is given as 15 degrees Celsius, and we know the uh, specific heats of both water and oil. So on substituting in the expression which we have got, so we can find out the water temperature and also the exit temperature of the uh, oil, which will come out to be 20.83 degrees Celsius. So similarly, what if you mix the oil with the water? So what will happen then? So in that case, your total internal energy will be uh, same, because the internal energy of water, there is no interaction with the surrounding. So the total internal energy, including both liquid, water and the oil, will be same. So the change in internal energy is 0. So it will be equal to MECE TE minus TI. So that is a change in temperature for water and change in temperature for oil. From this we can find out the final temperature or the equilibrium temperature as MCT. We are just rearranging it to find out the final temperature TE, which will come out again to be equal to 20.83 degrees Celsius. So this is the equilibrium temperature. This is true because even in the previous case, what you saw is the coil is so long that your exit temperature is equal to the water temperature. So this correspondingly, what it says is the water and oil has already reached equilibrium, and there is no much heat transfer happening after that. So that you can see here also. Here, after mixing both water and oil, this has reached an equilibrium state of same temperature of 20.83 degrees Celsius. So the second one was to find out the specific heat. So similarly, just like the previous one, your change in internal energy will be equal to change in enthalpy. So again, there, instead of liquid enthalpies, you will have for hydrogens. There the flow was liquid, so here it's hydrogen. So mass of hydrogen into specific heat of hydrogen. So in this case, we know all the temperatures. So we substitute here the temperatures, and we can find out the only unknown which will be there. The time is given, mass of hydrogen is given, and your specific heat is given. So from this, we can find out uh, the specific heat which is there for the hydrogen. This is one of the tough problems. I think I just took this to, so that even this case, you are ultimately what you will use is the first law and this thing. From that you can solve this problem. This uh, it's a very tough problem, but to show you and give a different kinds of problems, I have taken this problem. Any doubts in this?
हेलो सर।
Yes.
बट टॉपिक नेम क्या है? मैं अभी लेट आया ना, टॉपिक का नेम।
This to the week 5, the pure fluids, and you will have two phase and so on.
ओके
Your pressure equation of states and so on.
ओके
This is corresponding to the week 5.
ओके।
Okay. So moving on, you have a closed rigid tank filled with water vapor, initially at 20 megapascal and 520 degrees Celsius, is cooled until its temperature reaches 400 degrees Celsius. Using the compressibility chart, determine the specific volume of the water vapor in meter cube per kg at initial state, the pressure in megapascal at the final state. Compare the results of part A and B with the values obtained from the superheated vapor table. So we need to find out specific volumes between the two states and the pressure, and then also compare this with the values which you get from the steam table. So what they have given is state 1 is at 20 megapascal and 520 degrees Celsius, and it is cooled to reach 400 degrees Celsius. So this will be constant volume process. Again, this is a closed rigid tank with water vapor. So for water, we know that the critical points are, critical temperature is 647.3 Kelvin and critical pressure is 22.09 megapascal. So from this we can find the temperature as 793.647.3, which is a reduced temperature. 793 is corresponding to 520 degrees Celsius. So 520 plus 273 divided by 647.3. So the reduced temperature is 1.23. Correspondingly, reduced pressure is given is 20 bar at state 1, 20 by 22.09, which is the critical pressure, which will give me 0.91. So for this condition of reduced pressure and reduced temperature, from this figure, if you see at state 1, your reduced temperature is 1.23. So this is somewhere close between 1.2 and 1.3, and your reduced pressure is 0.91. So this is close to somewhere around 0.9 here. So correspondingly, your compressibility factor there will lie between 0.82 to 0.83. So from figure it will be 0.83, Z is 0.83. So compressibility, compressibility factor is Z is nothing but PV by RT. So from this we know P, we know temperature, we know R, and we also know compressibility factor. So we can find out the specific volume. So specific volume is nothing but Z into RT by P. Z is 0.83, R is 8.314 kilojoule per kilomole Kelvin, divided by your molecular weight to convert into kilojoule per kg Kelvin, and your temperature is known, and pressure 20 bar to 20 per so 20 megapascal, so 20 into 10 per 6 Newton per meter square. So substituting this, we'll get specific volume at state 1 as 0.0152 meter cube per kg, and correspondingly specific volume from the table is 0.01551. So if you see, it is fairly close, it's changing at fourth decimal.
Capital R is the universal gas constant or molecular gas constant?
This R is gas constant. If you have R bar or some other thing, that is a universal gas constant. So to find out gas constant, you are dividing it by molecular weight. For
Molecular
water, it is 18. So actual value is 18.02. Fairly you can
Okay.
take 18 also. So 8.314 divided by 18 to get gas constant. So the next one is to find out at state 2, since mass and volume, it's a closed system, mass and volume will remain same. So specific, it's a constant specific volume, you can say. So you can find out reduced specific volume. So reduced specific volume is specific volume into PC by RTC. So that is nothing but from similar to gas equation, PV by RTC. So V by Vc, specific volume at critical point. So from there we can find out your reduced specific volume is 1.12. So at state 2, this is constant specific volume lines. So this is 1.1 and 1.12. So it will lie somewhere in between. So at state 2 corresponding to specific volume of 1.12, and your TR is 1.04. At 400 degrees Celsius, your reduced temperature is 1.04. So at state 2, these lines are constant TR lines. So the dark lines are constant TR lines, and dotted lines is dash lines is constant volume lines. So correspondingly, you find out that your reduced pressure at state 2 is somewhere close to 0.68 or something. So from 0.69. So correspondingly, your reduced pressure is 0.69. You know the critical pressure. So reduced pressure is nothing but pressure by critical pressure. So multiplying by critical pressure, you will get pressure at state 2 as 15.24 megapascal. So that's what was asked. So moving on, we have a system consisting of 2 kgs of carbon dioxide gas initially at pressure of 1 bar and temperature of 300 Kelvin, which undergoes a power cycle with following process. Process 1 to constant volume to pressure of 4 bar, then process 2 3 expansion with PV raised to power 1.28. This PV raised to power gamma, so the gamma is 1.28, which is constant. Then process 3 1 constant pressure compression. So assuming the ideal gas model and neglecting kinetic and potential energy effects, sketch the cycle on a PV diagram and calculate the thermal efficiency. So if you see in a PV diagram, this is how it will look. So state 1 to 2, you are going a constant volume process to a pressure of 4 bar. From 2 to 3, you are following PV raised to power 1.28, and then 2 to 3, again you are doing a constant pressure process to reach state 1.
Sir, which book you are referring?
Sorry?
Which book you are referring?
See, I have taken problems from multiple books. There is no single book which I have referred.
Okay.
So you will find problems from many books. Okay, so first one is a constant volume process. So V2 equals V1. So they have asked you to use ideal gas equation assumption. So we can see that T2 by T1 equals P2 by P1. So we can find out temperature at state 2. Okay, so initial temperature is given as 300 Kelvin and 1 bar. So P2 is known, P2 is 4 bar, P1 is 1 bar, and T1 is 300 Kelvin. So substituting that, we'll find out temperature T2 is 1200 Kelvin. Further, using ideal gas equation, we can find out the volume. So volume is nothing but mRT by P. PV is equals to mRT. So mass is 2 kgs, which is given. R is again gas constant 8.314 divided by molecular weight into temperature 300 Kelvin divided by pressure 1 bar, which will give me 1 into 10 power 5. So this will give me volume of 1.134 meter cube per kg. So now using this, we can find out specific volume. So this PV raised to power 1.28. So we can find out specific volume at state 2 as volume divided by mass. So this will give me 0.567 meter cube per kg. And P3 will be equal to P1 because 1 to 3 is a constant pressure process. So we know state 2 pressure and volume. So we can find out specific volume at state 3. So specific volume is PV raised to power 1.28. So we can find out using that relation. So V3 is P2 by P3 raised to power 1 by 1.28 into specific volume. So this will give me specific volume at 3 as 1.675 meter cube per kg. So using this and ideal gas equation, we can find out temperature at point 3, state 3, which will come out to be 887 Kelvin. So next is we need to find out thermal efficiency. So for that, we need to find out how much heat which you are given and the work which you are doing. So we'll estimate work and heat transferred during all 3 processes, and we'll find out net work and net heat transfer. So for taking process 1 to 2, this being a constant volume process, so integral P dV, so dV is 0, so work done is 0 during process 1 to 2. So when you apply first law, it will come out the change in energy is equals to heat transfer minus work transfer. So work transfer is 0, so Q is nothing but mu2 minus u1. So you can use carbon dioxide table, or you can find out Cp of CO2, and this is taken from a refrigerant table for carbon dioxide. So Q is mass is known, so and internal energy can be calculated. Divide by this is values in kilojoule per kilomole. So to convert into kilojoule per kg, you are dividing it by molecular weight. So this will give me 1678 kilojoule. Then again for 2 to 3, the process is PV raised to power 1.28. So we'll integrate that. So P is constant by V raised to power 1.28. So on integrating, we'll get MR T3 minus T2 by 1 minus 1.28. So here we can substitute. We'll know T3, we know T2. So we can substitute and we can find out your work done is 422.4 kilojoule. So similarly, we apply first law. Sorry, did you ask anything? You have any query? Okay. So applying first law, uh, we can find out the heat transfer. So again, we can get U3 and U2. So each point we know both either specific volume and pressure or temperature and pressure. So we know two stage points, so we can easily find out the corresponding internal energy from the table. So U3 and U2 values, substituting that, and the work done which we have calculated 422.4. So on substituting that, we'll find out that heat transfer is minus 237.8 kilojoule. And then process 3 to 1 is a constant pressure process. So we know specific volume. This is volume. So we know specific volume at state 1 and 3. So we are multiplying by mass to convert it into volume. So this is nothing but equal to MR T1 minus T3. So either way you can use pressure and specific volume or temperature, and you will get your work done during process 3 to 1 is minus 221.8 kilojoule. The next is again we apply an energy balance, so we can find out heat transfer, which will come out to be minus 1240 kilojoules. So for the net cycle, work transfer is the summation of all the work during the processes. So this will be equal to 200.4 kilojoules, and the net heat transfer is minus 200.2 kilojoules. And so the problem is I think the heat transfer, if you see Q12 is 1678 kilojoule, and process 2 to 3, if you see, it is minus 237.8. so minus represents it's getting rejected, and positive it is supplied to the system. So heat which is coming in is positive, going out is negative, the other way around for work. So if you see 1678 kilojoule, you are supplying energy. So for efficiency is nothing but your net work divided by the heat transfer, heat which you supply. So W cycle divided by heat in. So heat in is, we know, 1678, and the net work which you get is 422.4 minus 221.8. So divide by heat transfer, heat supplied 1678. So this gives me efficiency of 11.95%. And if you see the net work done is minus 200.4 kilojoule, and the net heat transfer is 200.2. So in the cycle, if you see, your internal change in internal energy will be 0. So Q which is net Q which is going in is equal to net W. So that's what you can see. The slight changes because you are taking internal energy from the table, so there's a slight change in value because of this round off error. So your efficiency is 11.95%. That's what has been asked in the problem. Okay, any doubts?
No, sir.
Okay. Then moving on, a well insulated rigid tank, it contains of 1.5 kgs of refrigerant R134A. This is initially a two-phase liquid vapor mixture with a quality of 60% and temperature of 0 degrees Celsius. An electrical resistor transfers energy to the content of the tank at a rate of 2 kilowatt until the tank contains only saturated vapor. For the refrigerant, locate the initial and final states on a TV diagram and determine the time it takes in seconds for the process. So this is similar to a problem which we saw previously. So this is again a constant volume process. So it is initially at 0 degrees Celsius. You are supplying 2 kilowatt. There we found out.
Screen is not getting.
Sorry.
Okay, okay, now okay.
Okay. Uh, so in that problem we found out how much heat we supplied. In this problem the heat is given already, so which is 2 kilowatt, and of electrical work which is supplied to the system, and we know mass and quality initially. So this will go through constant volume process, and they're saying uh, to find out how much time does it take to convert the total amount of liquid plus vapor to saturated vapor. So since the volume is constant, so it's a constant specific volume process. So at state 1 we can find out the specific volume as using the same equation, using liquid saturated liquid vapor and saturated liquid and saturated vapor specific volumes, and we know quality is zero point 0.6. So substituting that, we can get specific volume as 0.04165 meter cube per kg, and correspondingly the internal energy at that state. These values are again taken from the R134A refrigerant chart tables. Substituting that, we can find out at state 1 it will be equal to 156.15 kilojoule per kg. Next, at state 2 we know that the specific volume at state 2 is equals to specific volume at state 1, and this will be equal to the saturated vapor specific volume. So using that, and from the chart you can interpolate it, and you will find that your temperature at that state 2 is equals to 15.16 degrees Celsius. So we know specific volume at state 2, so, and correspondingly we can find out temperature, and using that temperature we can find out the saturated vapor uh, internal energy, which is equal to 235.33 kilojoule per kg. So now, this being a closed system, we apply the first law, which is change in internal energy equals to Q minus W. So there is no heat transfer, but you are sending in work, which is the electrical energy which you are sending. So your change in W electrical is equals to M U1 minus U2. So which will be mass is 1.5 kgs. So U1 and U2 is known, from which we have calculated. On substituting, we will get electrical work is minus 118.77 kilojoules. So using this, so we know that we are supplying 2 kilowatts of electrical work. So W electrical divided by your rate of change in the internal energy. So W electrical into delta T will be equal to the total electrical energy which you are giving. So minus 108.77 divided by minus 2, which will give me 59.4 seconds. So we need to supply 59. It requires 59.4 seconds to change from initial 60% of vapor and liquid to fully saturated vapor. So any doubt? So I think this is my last problem. I'll see. So consider the system made of a cylinder closed by a piston, which is shown in figure. So the water contained in the cylinder at initial state 1 is first heated at constant pressure to the temperature T2. It is then cooled at constant volume down to pressure P3. So you can neglect both kinetic and potential energy, and you need to determine the thermodynamic state at each point. So you need to plot the process in a PV and TS diagram, then calculate the specific work involved and specific heat energy involved. So, so this is the system. You have a constant, you have piston, you have water, you have at state 1 you are going through two processes. First you are heating and then you are cooling at constant volume. So at first you are heating it such that your pressure is constant from state 1 to state 2. Then you are cooling this such that your volume is constant to reach state 3. So this is the change in process, and what is known is initially your pressure is 10 bar. So pressure 10 bar, you're changing from state 1 to state 2. Your temperature is 130 degrees Celsius initially. After heating it is reaching 200 degrees Celsius, and the final pressure is 2 bar. So thermodynamic states is given. So at 130 degrees Celsius and 200 degrees Celsius, your specific volume and enthalpy is given, and saturation state again for 2 bar and 10 bar is given. So you need to find out all the thermodynamic states and each point, and the specific work and heat energy involved, and we have to plot the process. So initially we will find out uh, the specific volumes and pressure. So the initially temperature T1 is smaller than, if you see, T1 is 130 degrees Celsius for 10 bar. So if you see, it is less than your saturation temperature, which is 179.88. So this is a subcooled liquid, so it is fully liquid. So at 179.8 you will have it's a saturated state. So if you can be either saturated liquid or saturated vapor or a mixture of that. So but at this state you are at 130 degrees Celsius and 10 bar, you are liquid but you are subcooled, so your temperature is less than your saturation temperature. So at that point the volume will be, there will be not much change. So it's, I think it's, yeah, so they have given that specific volume corresponding to 130 degrees Celsius and 10 bar, they have given specific volume as 0.0010696. So this is your specific volume and the corresponding enthalpy of the liquid, this is water, so 546.8. so we know both V and T, sorry, V and H. So specific volume is 0.0010696 and pressure is 10 bar, temperature is 130. So internal energy you can calculate H minus PV. So we know volume, we know pressure, substituting that we will get internal energy is 545.73 kilojoule per kg, and H1 is 546.8, which is given in the table. And then at state 2 they say it's a constant pressure process from 1 to 2. So your pressure is constant, so 10 bar, and the temperature is given as 200 degrees Celsius. So from table 200 degrees Celsius, if you see, this is again, it's a superheated state. So 10 bar, your saturation state is 179.88. So this is temperature is greater than 179.88. So now it says it is in superheated state, superheated vapor. So correspondingly 200, your specific volume is 0.2059 and enthalpy is 2826.8. So similarly you can find out internal energy, which is 2620.9 kilojoule per kg. So now state 3, they are saying you are cooling the system at constant volume. When you do it at constant volume, your pressure is final state pressure is given as 2 bar. So corresponding to 2 bar, uh, sorry, your specific volume will be same, because this now it's a closed system. This is a constant volume process. So the closed system, mass, there is no change in mass, so volume is constant. The specific volume will be same as V3 and V2. So initially we found out V2 specific volume is 0.2059. So if you go back to the table, your specific volume, your pressure is 2 bar and specific volume is 0.2059. So if you see corresponding to 2 bar, your specific volume of liquid is 0.001068. So it is less than your specific volume. And if you see specific volume of saturated vapor is 0.8854. So which is greater than your specific volume. So this states that you are lying in a two-phase state. So you are in you have a mixture of liquid and vapor. So corresponding to bar, we know saturated liquid and saturated vapor specific enthalpies, and you know the specific specific volumes of saturated liquid and saturated vapor, and specific volume at state 3. So substituting that, we can find out the quality. So quality is nothing but using the same expression for finding volume, you rearrange to find out quality. So substituting the values, you will get quality as 0.2316. So we'll get quality, and using this we can uh, and the saturated and liquid and saturated vapor enthalpies, we can find out the enthalpy H3 using this, and the saturated and the specific volume which we have calculated. We can calculate the internal energy at state 3, which is H3 minus V3 P3. So we can find out all the state values which are found out. Next is, we'll plot this in the PV and TS diagram. So if you see, this is a two-phase dome, and X3 is the constant quality line which is plotted. So initially you are at subcooled liquid. So you see it is far away, it is to the left of the saturated liquid curve. So you are in subcooled liquid. From there you are going a constant pressure process to state 2. You see this 2 is lying in a superheated state, and then from 2 you are coming down at constant volume to state 3, corresponding to this quality X3, which is we have found out as 0.2316. So this is how the state process will look in a PV diagram. So similarly in a TS diagram, so again this is your two-phase region, initially, and you are having a constant pressure line initially, because 1 to 2 is a constant pressure process. So one is you see this is again less than your saturated liquid state, and then from 1 to 2 you are going a constant pressure process. This again is straight line because this is a pure fluid, so your temperature, this thing, your pressure is your pressure will be constant during a phase change. So 1, and then your constant temperature, and then again temperature increases to state 2. So this is how process 1 to 2 will look. Then again you are coming back to the two-phase region, you are cooling again in a constant volume process. So this is a constant volume line, and X3 is your quality again, which is state 3, corresponding to pressure of 2 bar. So this is again 2 to 3 is your constant volume process. So this is how it will look in a TS diagram. Then we need to find out the work done and the heat transfer. Work done is nothing but P into dV, and for second process 2 to 3 it will be 0 because it's a constant volume process. So pressure into change in volume will come out to be 204.83 kilojoule per kg. So pressure is known 10 bar, a specific volume which I already calculated. So this is the specific work. This is 204.83 kilojoule per kg, and again second process is 0 kilojoule per kg. Similarly for heat energy, we'll apply the first law, and from there you can find out Q, which is change in internal energy plus your work done, so which will come out to be 2280 kilojoule per kg. And for state 32, so U3 minus U2 plus your work done here is 0, so it's just a change in internal energy, which will come out to be minus 1647.42 kilojoule per kg. So this is the work which your heat which you are taking out in cooling, and during 1 to 2 which you are supplying. So we have found out all the work done and heat transfer which was asked. Any doubts?
No, sir.
I think with this I have finished the problems which I prepared for today. If you have any doubts in the week or the previous weeks, you can ask, or else we can wind up the session.
Thank you, sir.